Okay, imagine this. You see a massive airplane wing, right?
Yeah.
And it's flexing in the wind during takeoff. Or maybe think about a giant turbine spinning like crazy. We see the outside forces, obviously, but what's actually happening, inside the metal,
Mm.
inside those parts, not just about pushing or pulling from the outside. It's more about how those forces create this really complex, hidden pattern of stresses within the material itself. You hear about things like concrete beams cracking, or, I don't know, shafts in machines suddenly failing. Often it really comes down to understanding these hidden internal stress patterns. So today we're doing a deep dive into a concept that's just, well, fundamental to almost everything engineered around us. It's called stress transformation. We've got a key chapter from an engineering textbook here. We're going to use it as our guide. We want to figure out how engineers kind of peel back the layers to find out exactly where and, crucially, in what direction those dangerous stresses are hiding inside a material. It's almost like being a detective, hunting for these hidden forces.
Right. And our mission for you today really is to give you a shortcut to understanding this whole area. It's critical stuff in mechanics. We'll try to simplify the complex ideas, maybe shed light on some surprising facts about why different materials break the way they do, and ultimately show you how engineers use this knowledge to keep us safe, basically, to ensure the reliability of buildings, bridges, machines, everything you rely on.
Okay, let's unpack this then, starting with the basics.
Mhm.
When engineers talk about stress, what exactly are we talking about?
So, stress is essentially the internal forces acting within a material spread out over its internal area. Think of it like the material's internal pushback against being deformed.
It's resistance.
Exactly. It's resistance to being pushed or pulled or twisted. Now, our source material points out something important. At any single point inside material, the stress isn't just one simple value. It's actually potentially quite complex. The general state of stress involves 6 different components: normal stresses, shear stresses, acting on different faces of a tiny imaginary cube inside.
Whoa, okay. 6 components. That sounds like a lot to keep track of for every single point.
It does, but here's what's interesting and frankly makes engineering feasible. In most practical scenarios, the forces, the loadings, are often coplanar.
Coplanar,
Yeah.
meaning in a single flat plane, like on a sheet of paper.
Pretty much, yeah. They act mostly within one plane, and when that happens, we can simplify things dramatically. We call it plane stress.
Ah, okay. Plane stress sounds better than 6 components.
Much better. It boils down to just 2 normal stress components. Those are the direct push-pull forces perpendicular to a surface and one shear stress component. That's more like a tearing or sliding force acting parallel to the surface. Just 3 things to track on, say, 4 faces of a little square element.
Okay, so plane stress simplifies things. That's a relief. But then, why do we still need to transform it? If it's already simpler, why not just stop there? What's the transformation part about?
That is the crucial question. Because even with plane stress, the values you measure, the suxy, texy, they completely depend on how you look at that point. Imagine taking an imaginary slice through the material at a certain angle.
Okay.
The very same physical point can show totally different normal and shear stress values if you just rotate that imaginary slice.
Really, just by changing the angle of the slice.
Exactly. Compare looking at it straight on versus looking at it tilted 30 degrees. The numbers change. Understanding this transformation lets engineers find the precise orientation, the exact angle where those stresses hit their absolute maximums or minimums. Finding those critical spots, those potential weak points, is absolutely vital for designing things that won't fail.
Got it. Okay, so before we get to the slick equations engineers probably use now, our source walks us through the fundamental way, the sort of step-by-step method.
That's right, the method of equilibrium. It's fantastic for building intuition, for really seeing why the transformation happens.
So how does that work conceptually?
Well, you start by conceptually sectioning the element, like taking an imaginary knife and cutting through that tiny square element at the angle you care about, let's say 30 degrees.
Okay, cutting it.
Then you draw what's called a free body diagram of one of the resulting pieces, usually a wedge shape. This diagram is just a clear picture showing all the forces acting on that piece, including the forces on the new cut surface you just made.
And these are internal forces, right?
Internal forces, now exposed. And remember, stress is force divided by area. So on your diagram, you represent these forces by multiplying the known stress components by the areas of the faces they act on. Finally, you apply basic physics, the laws of equilibrium. All the forces in one direction must sum to 0, and all the forces in the perpendicular direction must also sum to 0.
Balancing the forces.
Exactly. By writing down those balance equations, you can solve for the unknown stresses acting on your new angled cut surface, the transform stresses and texes.
Okay, let's try to make that more concrete. The source uses an example, right? Something about an airplane fuselage.
Yes, exactly. Imagine a specific point on the skin of an airplane. Let's say we know the initial stresses acting on an element aligned with the plane's axis. Maybe 80 megapascals pulling one way, 50 pulling another, and a 25 megapascal shear stress.
Okay, got the initial picture.
Now, what if we need to know the stress on an element that's rotated, say, 30 degrees clockwise from that initial alignment, maybe along a weld line or something?
Right, a different angle.
We'd use this equilibrium method. Cut the element, draw the free body diagram, multiply stresses by areas, which involves some trigonometry with a 30-degree angle,
Okay.
and then solve the equilibrium equations.
But what happens? Do the numbers change much?
Dramatically. The detailed calculations show that on one face of this rotated element, the normal stress becomes modical 4.15 MPa. That's actually compression, a pushing force, and the shear stress jumps to 68.8 MPa.
Wow, from 80 pulling to 4 pushing, that's a huge difference.
Yep. It is. And on the perpendicular face of that rotated element, it's negative 25.8 MPa normal and negative 68.8 MPa shear. The key takeaway here isn't just the numbers, but the principle. These are equivalent states of stress. It's the same physical reality at that point, just viewed from a different perspective, a different angle. But that different view might reveal the critical stresses.
Okay, so that manual method really shows you what's going on under the hood. But I can see how doing all those free body diagrams and trig calculations for every single angle would be tedious.
Oh, absolutely. It's great for understanding, terrible for efficiency and practice.
So for everyday engineering problems, there must be a faster way, right?
There is. And that's where the general equations of plane stress transformation come into play. They basically package up that whole equilibrium process into a set of formulas.
Formulas sound good. Faster.
Definitely faster. But before you just plug numbers in, there's one really crucial step: establishing a consistent sign convention. Rules for what's positive and what's negative.
Like defining your directions.
Exactly. Normal stresses are positive if they're tensile, pulling outwards. Shear stresses are positive if they act in the positive coordinate direction on a positive face, or negative on a negative face. It sounds a bit fiddly, but there's a standard diagram engineers use.
Okay.
And importantly, the angle of rotation, theta, is positive when you rotate counterclockwise from the original x-axis to the new x-axis.
Counterclockwise is positive. Got it.
Once you strictly follow these conventions, the equations there are specific equations for the new normal stress, the other normal stress, and the new shear stress become incredibly powerful. You just plug in your initial stresses and the angle, and boom, out come the transform stresses. No diagrams needed.
Okay, here's where it connects. Remember our airplane fuselage example? The one we just walked through with the manual method.
Yes, the one with the 30-degree clockwise rotation.
The source has another example, example 9.2, solving the exact same problem, but this time using these general equations.
Right. And what do you think the results are?
I'm guessing. Exactly the same as the manual method.
Precisely. The equations give you negative 25.8 MPa for the normal stress on one plane, and negative 68.8 MPa for the shear stress, and negative 4.15 MPa normal, and plus 68.8 MPa shear on the perpendicular plane.
Okay, that's really neat. It proves the equations work and shows just how much faster they are. It's like having a calculator versus doing long division by hand.
Exactly. It confirms the validity of the equations and highlights their efficiency for practical engineering work.
So we can transform stresses, we can do it manually to understand it, or use equations to do it quickly. But why? What's the ultimate goal here? Why bother transforming them at all?
Because engineers aren't usually interested in the stress on just any arbitrary plane. They're hunting for the extremes, the critical points.
The maximums and minimums.
Exactly. The absolute maximum and minimum stresses that a material experiences at that point, because that's often what failure initiates, where a crack starts or where the material might yield or crush. And this leads us to a really important concept: principal stresses, specifically in-plane principal stresses, usually called 1 and STU.
Okay, principal stresses, what are they?
These are the absolute maximum and minimum normal stresses occurring at that point within the plane we're considering. The biggest pull and the biggest push or smallest pull.
Max and min normal stresses, got it.
And here's something fascinating, a really fundamental property. On the specific planes where these principal stresses act, the shear stress is 0.
No shear stress at all. on those specific planes.
None. It's pure tension or pure compression on those principal planes. It's like finding the orientation where all the twisting or tearing action disappears, leaving only direct push or pull. This is a huge insight for design.
So how do you find these magical principal stresses in the planes they act on?
Yeah,
More equations.
you guessed it. The source provides specific equations. One set helps you determine the orientation of these principal planes, the angle, often denoted Phip, and another equation lets you calculate the magnitudes of the principal stresses themselves, 1 and 2.
Okay, let's connect this to the real world again. You mentioned concrete beams earlier. You often see cracks in them, right? How does this relate?
Ah, great connection. Those cracks you see in concrete, they're almost always caused by tensile stress. Concrete is strong in compression, but weak when you pull it apart.
Right, it crumbles under pulling.
Exactly. Now, using stress transformation, engineers can calculate the principal stresses at critical points in the beam. They can find unlan a maximum tensile stress, and the equations also tell them the orientation of the plane on which that maximum tension acts.
So they know the direction the crack will likely form.
Precisely. The cracks will typically form perpendicular to the direction of the maximum principal tensile stress.
Wow. So if you know where the maximum tension is and in what direction.
Then you know exactly where and how to place steel reinforcing bars, rebar,
Mm.
to counteract that tension and prevent the concrete from cracking. It directly informs structural design.
Okay, another example from the source, a shaft, maybe in an engine or machine just before failure. It has some initial stresses, a negative normal stress, compression, a positive one, tension, and
Oh.
some shear stress.
Right, a combined loading scenario. So the engineer's first step is often to find the principal stresses.
What does that tell them?
By plugging the initial stresses into the principal stress equations, they find the absolute maximum normal stress is, say, 116 MPa, and the minimum normal stress is minute of 46.4 MPa compression.
So a big pull and a moderate push.
Correct. And the equations also give the angles of the planes where these stresses occur, maybe 66.3 degrees for S1 and a netted to 23.7 degrees for side 2. And remember, on these specific planes.
No shear stress.
Exactly. Pure tension on one plane, pure compression on the other. This tells the engineer the shaft is most likely to fail, either by being pulled apart along that 66.3-degree plane or potentially crushed along the negative 23.7-degree plane. Now, normal stress is critical, but we can't forget about shear stress. That twisting, tearing action is also a major cause of failure, especially in certain materials.
Okay, so there's a maximum shear stress too.
Yes, the maximum in-plane shear stress, often called max. This is the highest shear stress occurring at that point within the plane we're analyzing.
And how does that relate to the principal stresses?
Here's another neat geometric fact. The planes where this maximum shear stress occurs are always oriented exactly 45 degrees away from the principal planes, where shear was 0.
45 degrees from the pure tension compression planes. Interesting.
It is. And there's an equation for this maximum in-plane shear stress, too, directly related to the difference between the principal stresses.
Now, when an element is oriented to experience this maximum shear stress, is there any normal stress happening too, or is it pure shear?
Good question. Unlike the principal planes, which had 0 shear, the planes of maximum in-plane shear stress do generally have normal stress acting on them as well. It's specifically called the average normal stress, and there's a simple equation for it too. It's just the average of the two principal stresses.
So max shear comes with an average normal stress on the same plane.
Okay. The source gives an example where they calculate this. Maybe a maximum in-plane shear of 81.4 MPa acting on planes where there's also an average normal stress of 35 MPa. Now, thinking about both principal normal stresses and maximum shear stresses raises a really important practical question.
Because?
Why do different materials fail in such dramatically different ways, even under the same type of loading? Think about stretching a steel rod versus stretching a piece of chalk.
Yeah, very different results. Steel stretches and necks down, chalk just snaps.
Exactly. This is where the type of material becomes crucial. We broadly classify materials as ductile, like mild steel, which can deform significantly before breaking, or brittle, like cast iron or chalk, which fracture suddenly with little warning.
And how does stress transformation explain their different failure modes?
This is where it gets really insightful. Our source provides 2 fantastic comparison examples. First, let's consider pure torsion, just twisting a bar.
Okay, twisting it.
If you take a mild steel bar, ductile, and twist it until it fails. Stress analysis shows the maximum shear stress occurs on planes perpendicular to the axis. And indeed, the steel fails due to shear often tearing along that plane, sometimes in a spiral pattern.
So ductile fails in shear under torsion. What about brittle?
Now, take a cast iron bar, brittle, and apply the exact same pure torsion. Stress transformation tells us that while the maximum shear is still on the perpendicular planes, the maximum normal tensile stress occurred on planes oriented at 45 degrees to the axis.
45 degrees?
Yes. And since brittle materials are weak in tension, guess how the cast iron fails?
It snaps along that 45-degree plane due to the tension.
Precisely. It fails due to normal stress, cracking cleanly at that predicted 45-degree angle. Same loading, different material, completely different failure mode predicted by stress transformation.
That's fascinating. What about just pulling on them axial loading?
Similar story. Pull on a ductile mild steel rod. Stress transformation shows the maximum shear stress occurs on planes at 45 degrees to the pulling direction. What do we see? The steel typically necks down and then fails along these 45-degree shear planes, forming a characteristic cup and cone fracture. It fails in shear.
Okay, ductile fails in shear under tension too. Brittle.
Pull on brittle cast iron. Again, it's weak in tension. Stress transformation shows the maximum normal tensile stress is simply on the plane perpendicular to the pulling direction. And indeed, the cast iron just snaps cleanly straight across that plane. It fails due to normal tensile stress.
Wow.
So what's amazing here is that our stress transformation analysis, finding principal stresses and maximum shear stresses and their orientations, perfectly predicts these distinct failure angles and modes for different material types. This really highlights why understanding these maximums is so critical for choosing the right material for a job and predicting how it will behave under load.
Okay, all these equations for transformation, principal stresses, max shear, it's powerful stuff, but maybe a little abstract to visualize just hearing the formulas. Is there a way to, see it?
Absolutely. And engineers have a truly brilliant graphical tool for this exact purpose. It's called Mohr's circle.
Mohr's circle. Sounds intriguing.
It is. It was developed by a German engineer, Otto Mohr, back in the 1880s. It's an incredibly elegant way to visualize and even calculate stress transformation.
So what does it look like? How does it work?
Imagine a graph. The horizontal axis represents normal stress, and the vertical axis represents shear stress.
Okay, horizontal, vertical.
Mohr's circle is literally a circle plotted on this graph. And the beauty is every single point on the circumference of this circle represents the state of stress, a specific Sumpton value, acting on a specific plane through your point of interest in the material.
So the circle contains all possible stress states for that point just by rotating the plane.
Exactly. As you conceptually rotate the plane you're looking at in the real material, the corresponding stress state traces around the circumference of Mohr's circle on the graph. You can literally see how normal and shear stress change together.
That sounds really useful. Is there a trick to how the angles relate?
There is, and it's the key to using it. A rotation of your physical element by an angle in the real world corresponds to a rotation of 2 times that angle, 2 on Mohr's circle, in the same direction.
Double the angle on the circle. Okay, gotta remember that.
Great. So how do you draw it? It's surprisingly simple. First, you calculate the center of the circle. It always lies on the horizontal normal stress axis, and its position is just the average normal stress.
Like plus AC2.
Okay, find the average normal stress. That's the center.
Then you need one point on the circle to define its size. You plot a reference point based on the known stresses on one face of your initial element, say the X face. This point has coordinates. Remember, the sign convention for shear is slightly different for plotting on the circle, but it's a standard procedure. Plot the center. Plot a reference point.
The distance from the center to this reference point is the radius r of the circle. Now you can draw the whole circle.
And once it's drawn, what can you see immediately?
So much. The points where the circle intersects the horizontal axis, those are your principal stresses, 1 and 2, because at those points, the shear stress, the vertical coordinate, is 0.
Visually finding the points of 0, shear. Clever.
And the very top and bottom points of the circle, their vertical coordinates give you the maximum in-plane shear stress, max. The radius of the circle actually is the maximum in-plane shear stress.
Wow. So the center tells you the average normal stress, the radius tells you the max shear, and the intercepts tell you the principal stresses.
Exactly. It lays it all out visually. The source has examples showing this for, say, a solid shaft, instantly reading off the principal stresses. Or, for another element, seeing the max shear and average normal stress pop right out from the circle's geometry.
That's cool.
Yeah.
But can it do more? What about finding the stresses on just some random angle, like that 30-degree rotation we talked about earlier?
Yes, that's another major advantage. Let's say you know your initial stress state, your reference point on the circle, and you want to find the stresses on a plane rotated 30 degrees counterclockwise. 3
Well,
plus 30 degrees.
okay.
You just rotate from your reference point on Mohr's circle by twice that angle, so 2 coincidentally 60 degrees in the same counterclockwise direction.
Rotate 60 degrees on the circle.
And wherever you land on the circumference, you just read off the coordinates of that new point. The horizontal coordinate is your new normal stress, and the vertical coordinate is your new shear stress for that 30-degree rotated plane.
So you can find the stress state for literally any orientation just by rotating around the circle.
Precisely. Example 9.9 in the source shows exactly this, taking an initial state, rotating by 2 on the circle, and reading off the transform stresses. It turns complex trigonometric equations into simple geometry on a graph.
Okay, Mohr circle sounds like a fantastic tool for visualizing and calculating these in-plane stresses. Principal stresses, max in-plane shear. But you mentioned ductile materials failing due to shear earlier. Is the in-plane max shear always the absolute highest shear stress the material experiences? Or could there be an even higher shear stress acting somehow out of that plane?
That is an excellent and critical question, especially, as you said, for ductile materials whose strength is often governed by their ability to resist shear deformation. And the answer is, sometimes the true absolute maximum shear stress at a point occurs on a plane that is out of the original 2D plane we've been analyzing. We need to consider the full 3D stress state, even if we started with plane stress.
Uh-oh, so looking just in 2D might not be enough to find the real weak spot.
Potentially, yes. You need to consider the stress state on all 3 dimensions, which means considering 3 principal stresses, where some D is a principal stress perpendicular to our original plane. For plane stress, 3 is typically 0.
Okay, so we have 1 and 2 from our plane stress analysis, and 3, which is often 0. How do we find the absolute maximum shear from these 3?
Our source material nicely breaks this down into 2 key scenarios based on the signs of the in-plane principal stresses that we already found.
Scenario 1. What if the 2 in-plane principal stresses, so 1 and 2, have the same sign, meaning they're both tensile, both positive, or both compressive, both negative?
Okay, in this case, and remember, center is 0, the absolute maximum shear stress will occur on planes oriented 45 degrees out of the original xi plane.
Out of plane, okay. And how big is it?
Its value is calculated based on the difference between the largest principal stress, either 4 or 2, whichever is bigger in magnitude, and 3, which is 0. So it's simply half of the numerically largest in-plane principal stress.
Half the biggest principal stress.
Right. The source gives an example of a pressure vessel where S1 and S2 are both positive tension. The calculated in-plane maximum shear stress is one value, but the absolute maximum shear stress occurring out of plane is actually larger. So ignoring the 3D aspect would underestimate the true maximum shear.
Okay, that's scenario 1. Same signs mean look out of plane. What's scenario 2? When the in-plane principal stresses have opposite signs, one tensile positive, one compressive negative.
Right. In this common scenario, the absolute maximum shear stress turns out to be equal to the maximum in-plane shear stress that we already calculated, which is 3, 2.
Ah. So if they have opposite signs, the maximum shear we found using our 2D analysis is the true absolute maximum. We don't need to look out of plane.
Exactly. The critical shear failure plane is within the original plane of analysis. The source shows an example of a machine shaft where S1 is positive and S2 is negative. The calculated absolute maximum shear stress perfectly matches the maximum in-plane shear stress.
So let me see if I've got this, if we connect this back. Determining if the principal stresses, so 1 and 2 have the same sign or opposite signs is crucial,
Yes.
because that tells you whether the real danger zone for shear failure, especially in ductile materials, is within the plane you analyzed, or if you need to consider planes oriented out of that original view.
Precisely. It's about finding the true maximum shear stress wherever it may occur in 3D space. This understanding is absolutely critical for ductile materials, helping engineers pinpoint the actual weakest point in a design and ensure it can withstand the loads without failing in shear. It's like having, as you said earlier, X-ray vision for potential failure modes.
Wow. Okay, what a journey we've taken in. We started with just the basic idea of internal forces stress at a single point. Then we dove into how engineers transform those stresses, looking at them from different angles to understand how they behave in all sorts of orientations. We saw the step-by-step equilibrium method, the powerful equations, and even that really neat visual tool, Mohr circle, for making sense of it all.
And I think most importantly, we've connected these concepts, which can seem a bit theoretical, back to the real world. We saw why engineers care about principal stresses and maximum shear stresses because
Yeah.
they dictate how things actually fail. We saw how ductile materials like steel and brittle materials like cast iron behave completely differently under the same loads, failing due to shear or normal stress, respectively, exactly as predicted by the analysis. And we learned why distinguishing between in plane and that absolute maximum shear stress is so vital for safe, robust design, especially with ductile materials.
Yeah, it really drives home that this knowledge isn't just, academic stuff in a textbook. It's truly the bedrock. It's what allows engineers to design bridges that actually stay up, airplane wings that don't rip off, and even just the simple tools we rely on every day to work safely and effectively.
Yeah.
It feels foundational.
It absolutely is. So, next time you look at a structure around you, maybe it's a big crane lifting something heavy, or the crank on your bicycle, or even just a simple bolt holding something together, take a second to consider that invisible, intricate dance of internal forces happening deep inside the material. Understanding stress transformation, even conceptually, fundamentally changes how you perceive the strength, the design, and the hidden complexities of the engineered world all around us.
So, thinking about everything we've unpacked today, what's the one thing that really stands out to you? How does this deeper understanding of these hidden internal forces change how you appreciate the engineering that, well, shapes pretty much everything in our modern world? Something to think about.